This is all about collisions and the conservation of momentum. And this is the bulk of what we're going to be doing with momentum, so we'll start with just one-dimensional and then eventually we'll move into two-dimensional. So whenever we say conservation of momentum, we're referring to the law of conservation of momentum, which states that for any collision occurring in an isolated system, momentum before the collision is equal to momentum after the collision. And by isolated system, that means we have no other outside forces that are acting on the system. The equation for conservation of momentum, and this is messy. Let's start with the simple. Your momentum before the collision, I'm going to call that PA, is equal to your momentum after the collision, so PB. So A, and I know this is confusing, refers to before collision, and B refers to after collision. Okay, so breaking apart the P's. P is momentum, which is mass times velocity. So that means your mass times your velocity before the collision is equal to your mass times your velocity after the collision. But if there's a collision, that means you're going to have more than one object. So mass of object 1 times the velocity of object 1 before the collision plus mass of object 2 times velocity of object 2 before the collision equals mass of object 1 times velocity of object 1 after the collision plus mass of object 2, velocity of object 2 after the collision. So m1v1a plus m2v2a equals m1v1b plus m2v2b. So these are the mass of each object. And if you have more than one object, we will see a three-way collision, then you would just add in a third plus m3v3a and b. So this is the mass of each object. And then the v's are the velocities of each object. And velocity, because the direction here will matter. And again, A refers to before the collision, B refers to after the collision. So momentum before is equal to the momentum after. You will have this equation on your formula sheet. So this very long thing with all the subscripts, again, this is, I think, is the easiest way to look at it. You will have it. I'm going to go now and look at 3 different kinds of collisions and give you the case, so in other words, what this equation will become for each of those 3 collisions. And then I'll do 3 examples, one for each type. So 3 types of collisions. The first one we have is an elastic collision. In an elastic collision, objects have different velocities before, they bounce off each other, and then they're going to have different velocities after the collision. In other words, kinetic energy is going to be conserved in an elastic collision. And because they have different velocities before and different velocities after, the equation is exactly what we had on the last page. So m1v1a plus m2v2a equals m1v1b plus m2v2b. So this shows that there are 2 different velocities before and 2 different velocities after. The next type of a collision is inelastic collision. And this is where objects are going to have different velocities before the collision, but they're going to combine or stick together and have the same velocity after the collision. Here, kinetic energy is not conserved. So what does this equation become? Different velocities before the collision, so m1v1a plus m2v2a equals the same velocity after the collision. So that means that v1b equals v2b, and we can just call that vb. So this would be m1 vb plus m2 vb becoming m1 v1a plus m2 v2a equals m1 plus m2 VB. Essentially what's happening, you have two objects combining to become one. So when we combine those two objects, we're going to combine their two masses. And because they're now one and sticking together, they'll have one speed with one giant mass. Our third type of a collision is not really a collision, it's called an explosion. So I use the word collision lightly here. But here they're going to have the same velocity before, and then they're going to be pushed apart or exploded apart somehow, and they're going to have different velocities after. And in this case, because you're adding velocities here, the kinetic energy will be gained. So you're adding kinetic energy into the system when you have an explosion. So in this case, they have the same velocity before, so V1A is equal to V2A, and I'm just going to call that VA. And this is the exact opposite of an inelastic collision. So you have M1V1A plus, this is M1VA plus M2VA equals M1V1B plus M2V2B. So again, exact opposite of an inelastic collision. Now on the left-hand side, we have a combined mass, M1 plus M2, times VA, because they have the same speeds before, equaling M1 V1B plus M2 V2B. So this, you don't have to memorize, but you're also not going to get it. This can always, always, always be derived from the big, long conservation of momentum equation. So let's do 3 examples, one for an elastic collision, one for an inelastic, and then one for an explosion, and we'll see how these equations work. So first, a hockey puck moving with a velocity of 35 meters per second hits a second puck initially at rest. Both pucks have a mass of 1 kilogram. If the pucks stick together, how fast are they moving after the collision? You need diagrams for every single one of these problems. Reason you need the diagrams, because momentum depends on velocity. Velocity is directional. You need the diagram to show the direction. So here's the hockey puck. I'm going to call that puck 1. It's initially moving, and puck 2 is initially at rest. And this is A before the collision. Then puck 1 hits puck 2. They stick together, and then they're going to move. And we'll call that B. Given information. V1A. So in other words, the speed of puck 1 at A equals 35 meters per second. V2A, so the speed of puck 2 at A, it's at rest, so 0 meters per second. Both pucks have equal mass, so M1 and M2 are both 1 kilogram. They stick together, so because they stick together, we know this is an inelastic collision. So this is inelastic, meaning they'll have the same speed after the collision, so we're looking for VB. Inelastic collisions, M1V1A plus M2V2A equals M1 plus M2 VB. V2A is initially 0, so this becomes pretty simple. Rearranging to isolate for VB, we get M1V1A over M1 plus M2 equals VB. So my mass is 1 kilogram times V1A, 35 meters per second, over 1 kilogram plus 1 kilogram equals VB. So 1 times 35 is 35. 35 over 2 is equal to 17.5 meters per second. There are 2 sig figs. I'm out of room. So VB is approximately equal to 18 meters per second. I mentioned how important the diagrams are for direction. I show it moving to the right, which makes this a positive velocity. As they collide, since they're equal mass, it's assumed that they're probably going to be moving in that same direction to the right. Because my number turned out to be positive, it also agreed with my diagram, so it makes sense. If I drew everything going the opposite way, so if everything was moving to the left as opposed to the right, then this answer would have been negative. So that's why you need the diagram whenever you do these problems. All right, let's do the next two examples. So here we have a 125 kilogram astronaut who throws a 2.3 kilogram hammer at a velocity of 12 meters per second. Assuming both the astronaut and hammer are initially at rest, how fast will she recoil? And remember, recoil just means move backwards. So the astronaut is in space, holding on to the hammer. Call the astronaut 1, the hammer 2, and this is A. They're both at rest. She then throws the hammer. So the hammer moves this way, and she moves the other way. So she's 1, hammer's 2, and we'll call that B. Given information. Mass of object 1. It does not matter what you make 1 or 2. I just chose to make the astronaut my object 1. So mass of object 1 is 125 kilograms. Mass of object 2, 2.3 kilograms. Before the collision, they're both at rest, so V1A equals V2A equals 0 meters per second. And after the collision, she throws the hammer, so V2B at 12 meters per second. And given all that, we're looking for how fast the astronaut moves. So we're looking for V1. B. Okay, so because they're initially at rest, both initially at rest, this is an explosion because they have the same velocity before. So M1 plus M2 VA equals M1 V1B plus M2 V2B. They're initially at rest, that goes to 0. This becomes very simple. We're looking for V1B, so isolating for that. Negative M2 V2B over M1 equals V1B. Negative 2.3 kilograms times 12 meters per second over 125 kilograms equals V1B. And this will come out to negative 0.2208 meters per second for V1B. Why is it negative? Because according to my diagram, she threw the hammer to the right and she recoiled, which means that she had to move to the left. Left is negative velocity, so the numbers work out. This is 2 sig figs, so V1B is approximately negative. Again, the negative matches up with my picture. I can't ignore it. Negative 0.22 meters per second. Okay, last example will be for the third type of collision, so an elastic collision. We have a 2.5 kilogram cart moving at 2 meters per second to the right. It strikes a 3.5 kilogram cart moving at 3 meters per second in the opposite direction. If cart 1, so we'll call this one cart 1. If cart 1 recoils with a speed of 4 meters per second, how fast is cart 2, so that's the 3.5 kilogram cart, how fast is cart 2 moving after the collision? Diagram. So cart 1 is initially moving to the right. Cart 2 is initially moving to the left, and this is at A. They're going to collide and bounce off each other. So now cart 1 will move to the left, we assume, and cart 2 will move to the right. The one thing about elastic collisions is you're never going to know exactly what way they move afterwards. So because of that, this part of the diagram would be arbitrary. It does tell us that cart 1 moves to the left, so we do know that. We don't know for sure if cart 2 will move to the right. We can assume, but when we do the math, that's when it'll work out and tell us exactly what the direction is. So we have M1 V1A plus M2 V2A equals M1 V1B plus M2 V2B. Nothing cancels out here and it doesn't simplify, so we do have all of these values. It's just a matter of doing the algebra and then putting the numbers in. We're solving for V2B, so I'm going to isolate that. We get M1 V1A plus M2 V2A minus M1 V1B over M2 equaling V2B. And let's just put all the numbers in because we already have everything. So M1, 2.5 kilograms times V1A, 2 meters per second, plus M2, 3.5 kilograms, times V2A, negative 3 meters per second, minus 2.5 kilograms times negative 4 meters per second, all over 3.5 kilograms, equals V2B. So 2.5 times 2 is 5, plus 3 times 3 is, plus 3.5 times 3 is 10.5, plus 2.5 times 4, so 10. These are all pretty simple numbers, divided by 3.5. This all reduces down to 1.285, keeps on going. Units. Kilograms all go away. We're left with meters per second. That makes sense since this is a speed that we're solving for. So V2B is equal to 1.25, keeps on going meters per second. This worked out to be a positive number, so that means that the second cart does move to the right after the collision, so it does bounce and recoil in the opposite direction, same as cart 1. We only have 2 sig figs, so V2B with 2 sig figs is approximately 1.3 meters per second. So these were 3 examples for the 3 different types of collisions. With elastic collisions, you do again use this whole equation, but many times one of the 4 terms will cancel out. If it doesn't, then it's really just the algebra and making sure that you don't mess up your subscripts with your 1s and your 2s and your A's and your B's.